Hi. So today we're going to talk about static single assignment, or SSA for short. So from the last lecture, there are a few concepts I want you to remember. It is essentially what it means to be a loop, even though you're probably familiar with it. The basic concept, and we learn about it in the class and its formal definition. Then dominator tree, natural loops, and back edges. So the summary of finding the loop, first of all, what you need to remember, what does it mean to be a loop in the graph theoretic terms? We come up with definitions and algorithms to build the graph based on dominator tree, back edges, and the definition of natural loops. That's what's important in this part. So I'll remind you how we find back edges. So we first do a depth first spanning tree, edges traversing a depth first search, and we essentially categorize edges in three categories. There are advancing edges from ancestor to proper descendant. There's some cross edges that can go from the right to left, and retreating edges, edges that go from descendant to ancestor. So they're not necessarily proper. So this is an example how we can mark this graph. Remember that advance and cross edges might depend on which order you traverse, but retreating edges are not. And that's what's the key to identify correctly here. So not every retreating edge is a back edge. So for the back edge, there's additional requirement. The tail should be dominated by the head. So essentially, we perform a depth first search, and for each retreating edge, we check if H is in its tails dominator list. If it is, then that's a proper back edge. And the most programs with all good structured code, and even most go-to programs, have so-called reducible flow graphs. It means that retreating edges, the number of retreating edges is equal to the number of back edges. And in non-reducible graphs, this is not true because retreating edges might not be actually be a back edges. And this is an example of non-reducible flow graph. We look at several examples of different control flow graphs, and we colored the edges. And as you can see here, we get the retreating edges, so it's all relatively straightforward. We then can construct natural loops. So the natural loop of a back edge is essentially the smallest set of nodes that includes the head, the tail of the back edge, and has no predecessors outside the set, except for the predecessors of the header. And we defined an algorithm in the class that was relatively straightforward again, where you essentially find all the body of the loop in an iterative manner. So the inner loops are the loops that where there is no other loop within that loop. So essentially, if you have two loops, if they don't have the same header, they either disjoint, so they don't overlap, or one is entirely contained, nested within the other inner loop. If two loops share the same header, it's hard to tell which one is the inner loop, so usually we just combine them as one, but that's a rare situation. And to simplify the optimizations, we also create a special control flow node called pre-header. So the pre-header is essentially a basic block for every loop, and we put it right before the header, and we redirect all the input edges in the control flow graph from the header to the pre-header. So the header has only one input edge. That simplifies optimizations in the header. Okay, so this is just some material to refresh your memory from the last class. And today we're going to talk about static single assignment. In order to understand why single static assignment is useful, we first look at the types of questions we want to ask when optimizing the code. One example is loop invariant code motions. So imagine you have a loop like that, And this box here may represent actually multiple basic blocks, and there is a back edge here. And we might ask questions like, are variables B, C, and D are only defined outside of loop? If that's the case, we can move this expression fully outside of the loop, because the expression B plus C also would be completely defined outside of the loop. So that means it's redundant to compute it here. You can just move it out. If that's the case, and it turns out that other definitions of A are inside the loop, then there are other optimizations we can do. Then if all uses of A inside the loop, then, and if say we can prove that that's the only definition, then we can find that, say, going from B plus C into here plus D would lead us to a situation where this is also invariant inside the loop, but we can move this out as well. So overall, you can see that understanding where each variable is defined can lead to powerful optimization, such as loop invariant conmotion. Another example, optimization is copy propagation. So essentially, if we had this traditional hammock here, we have x assigned to y, and then here we use x. So what we want to understand are what are the all-reaching definitions of x. If they happen to be all the copies of the same variable, x equal y, and y is not redefined since that copy, then we can just substitute x with the use of y. It would be nice if we can collect this information and can traverse directly between related uses and defs. This would enable a form of sparse code analysis, so we can skip or don't care cases. Appearances of the same variable may be actually unrelated. So that's another problem that we would like to deal somehow. For example, in this piece of code, you see the variable x is used in this basic block. It's defined and then immediately used. And then x is used much later, again in this basic block, and defined and then used. These values x has nothing to do with each other, so conceptually we could just use them separately with a different variable. Compiler could use renaming to make the different versions more explicit. So instead of using x in both cases, we can use x1 and x2. Okay, so how can we collect this information? The first simple way that people can deal with this is using use definition chains and definition use chains. So what is a use definition chains? Use definition chains is a special structure that for a given definition of variable x, it answers the questions what are all of its uses. And definition use chains are the other way around. For a given use of variable x, it says what are all the reaching definitions for the variable x. Unfortunately, even though DU and UD chains were used quite extensively in 80s and early 90s, people quickly realized they can be very expensive. Let's consider this code here. We had these two switch statements. In one switch statement, x is defined, and another statement, x is used. As you can see here, if we just gonna follow the definitions, we row down there is a tons of edges we're gonna have for each def and for each use. So we're gonna have like plenty of elements in each DU chains. In fact, if we carefully look at it, we're gonna see that it grows linearly both with the number of defs and with the number of uses. So we get 0 of nm in both space and time. One solution here could be limit each variable to one definition site. So something along these lines might be helpful. With this idea in mind, static single assignment was proposed. Static single assignment is an AR where every variable is assigned a value at most once in the program text. So easy for a basic block, because that's essentially a value number in algorithms that we faced before. We can visit each instruction in program order, and we can assign left-hand side to a fresh version of the variable and right-hand side for the most recent version of each variable. As the results, what we're going to get is we can get a 1 here definition, and then 1 here, a2 here, a2 here, and a3 here, and so on. It's relatively straightforward. We did it before. So it seems to be very straightforward. Unfortunately, there is a challenge. Whenever there is a join in the control flow graph, it's not clear which assignment of the variable to use. For example, look this piece of code. We had a1 here, right, defined here and used. So that value a1 can reach this place, but also a2 can reach this place. So which one to use, a1 or a2? Or similarly for C, I had C2 reach this way and C1 reach this way. So this complication is fundamental and has to be resolved somehow. And the way it's resolved in SSA is by using a new notational fiction called phi function. The phi function is a non-existent element that was created for convenience. It's a part of the intermediate representation. But it's not, one important thing to remember, that it's not going to be something that would be generated in the final code because there's no instruction like phi. So the phi node is a temporary IR construct that eventually will go away as we start to generate the code. It will be either fully removed with all the information not being needed anymore, or will be replaced with some copy instructions. So essentially for this piece of code, we're going to generate 3 phi functions, one for A, one for C, and one for B. As you can notice, for B, there's a question mark here. Why this happens is because one value of B comes from this definition, but under this path, there can be undefined value of B that we really don't know what's defined to. This is where the question mark is coming. Okay, this is their more or less informal definition of phi function. So what is the formal definition? The formal definition is that the phi function merges multiple definitions along multiple control flow paths into a single definition. At a basic block with p predecessors, there are p arguments to the phi function. So that means if my node has p predecessors, I have certain number of axes along the different input edges, and the output of the phi node is a new x that generates a new definition in this basic block. So how do we choose which xi to use in each case? Because it has multiple of those. Well, the beauty of it, we don't really care. I have the information, I know which x coming along this edge, but in most cases, I don't really care which one is used. As soon as I have the new definition that I can use in this basic block, I have all the information needed to resolve their to resolve the definitions that comes across each incoming edge, it means I had all the information needed, right? I don't really need to resolve it all the time. Instead of thinking which of this value is at each particular case, I can just use this x new, right? So the question is how to implement it properly. So one part of the implementation, obviously we need to generate all the copies here. So essentially A3 copies to A1, C3 copies to C1, A3 copies to it, and so on. So this is to align with these phi functions here, right? So this is essentially how they implemented as copies. So how are we going to find them? How are we going to find SSAs and where to place them? Well, there is such a thing called trivial SSA. We can essentially make each assignment generates a fresh variable, and at each join point, we insert 5 functions for all live variables. So for example, for a code like that, for a hammock, as usual, we're going to generate a 5 function for x and 5 function for y, because both x and y are live at this point, and we had a merge, right? Here, join point. Unfortunately, that can be extremely wasteful because we're going to generate a lot of 5 functions that are not needed. For example, here, this 5 functions is not needed because both values here I form across both edges x1, and there's no change in the value of x1. So what we really want to generate is a so-called minimal SSA. So essentially, each assignment generates a fresh variable, and at each join point, we insert 5 functions for all live variables with multiple outstanding definitions. Here's another example. You see the variable c is both defined and used in this basic block, and there's a back edge here. What it's going to lead to is, because there is a back edge here, I'm going to have a, as you can see, a phi node that's going to use variable c2, right? C2 would be coming here from the back edge, and also C1. C1, that would be the variable coming along this undefined path, right? A key question here is, where do we insert 5 functions? For example, if there is a def of A in block 5, which nodes need a phi node? Let's first try to understand fundamentally where we need to insert 5 functions, and then try to devise a practical algorithm to do it. We really want to insert a 5 function for a variable A in block Z if and only if A was defined more than once before. That means there is a path here and path here. Then we want that there exists non-empty path from X to Z, so path from X to Z is needed, and a non-empty path from Y to Z, such that the intersection of this path is just block Z. So it's the first basic block where these two paths meet. So block Z is common across both paths, and at least one path reaches Z for the first time. So this means it's a path convergence. If that's the case, we really need to have a phi node for variable v here, because it essentially both passes reaches this place. It's the first time when they merge, they're really two different definitions. We have no way other than defining f5 functions here. One important property of SSA that definitions dominate uses. It sounds very simple, but it's a very helpful property. For example, if xi is used in a phi function, what it really means is that basic block xi, right, for this def, dominates ith predecessor of the basic block where the phi node is located. If you have this regular assignment without phi function, it really means that the basic block x dominates basic block y. We can use this property for an efficient algorithm to convert into SSA. What we need for that, we need to build the concept and utilize the concept that we already have before, dominance tree. Take the control flow, build the dominance tree. And I remind you that strictly domination means that x has to dominate w and x is not equal to w. So if there is a definition of A in block 5, which nodes need a phi function? So to help with that, we need to look at the so-called dominant frontiers. So we're going to see at which nodes block 5 dominates. This is block 6, 7, and 8. This is easy. Then we're going to look for something called dominance frontier. The dominance frontier for a node X is essentially such nodes W such as X dominate predecessors of W, and X does not strictly dominate the W itself. What does it mean in practice? It means I'm looking for all such nodes such that their predecessors are here, right, in this yellow, but they had another path that doesn't go through 5, so 5 doesn't dominate them. Why is that important? Well, what it really means is that if I look at this block, and there's a definition here, this is the first place outside of the dominance frontier of basic block 5 where, as you can see, I might need a phi node, because here everything is dominated. If A is defined here, I don't need to change anything here. Everything is dominated, so I'm just going to be use the value A. But here is the first place where I exit out of the dominance subgraph for 5, and there's another path. So I had A defined here, and A can be defined also here. So it means I really need to find out here. So this is the earliest possible places that's needed to generate phi nodes. As you can see here, this is really shows why for each of these nodes I need a phi node in there. Using a dominance frontier to compute SSA, it really boils down to two parts. Place all phi nodes in the right places and rename all the variables. So I'm not going to go into details of these algorithms, but it's relatively straightforward. Essentially, the way you build a dominance frontier, you go and gather all the depth sites for every variable, and then for every variable and for each depth site, you look for its dominance frontier, and if we haven't put phi node in the node yet, then we put one. And if this node didn't define the variable before, then we had to add these nodes to the depth site. This essentially computes dominance frontier in the iterative fashion on the fly and inserts the minimal number of phi necessary. There is no unneeded phi nodes entered. This is the formal definition of this algorithm. I'm going to skip this. So do not make it too complicated. You can go over that. It really just formally describes what I informally described in the previous slide. The renaming of the variables is also relatively straightforward. You work through the dominance tree and rename the variables as you go. You replace the uses with more recent renamed definitions. For straight line code, this is really easy. What if we have branches and joins? Then we need to use the closest def such that the def is above the use in the dominance tree. And as you remember, we already have the dominance tree, and we know by their construction of the SSA node, there's always something that dominates it. So you just need to find the closest def. So how would you compute the dominance tree? So for this graph on the left hand, it's very straightforward. So from 1 to 2 is your dominance tree. From 2 dominates 3, 2 dominates 4, right? 3 dominates 5, 6, and 7. You cannot go to them because of going to 3. So for these dominators, for these nodes 1 to 7, we can get dominance frontiers. As again, for this simple graph, it's relatively simple. For 2, the dominance frontier is just the node 2 itself. For 5, the dominant frontier is 7 because there is a path like that, right? Then for 6, it's also 7 because there's a path like that. And for 7, the dominant frontier is 2 because if you look at this edge, there is another path here, right? Okay. We can then, for each variable I, j, and k, we can look at the original definitions and we look at all the def sites and we can just iteratively in this algorithm work for each variable and find what are the dominant frontiers is and where do we need to insert the phi function. For example, for variable I, it's straightforward to just, the first block, and then for j, you go to block number 1, then from block number 1 you go into 5, from 5 you go into 7, and then 7 goes into your, the working group here for j from 1 to 5. From 5, 6, it become 1, 5, 6, 7. And as you go, you start to add the 5 functions. So you add it in here, you add it in here, and then you stop at 6, and you do exactly the same thing for k, because k is really symmetrical here with respect to definitions. You get pretty much the same thing as before. And then you do the variable renaming. Again, this is a very straightforward process. You just, as you go, you just rename the variables. Each time you see something not renamed, you just give it a new name and reuse it along the dominance path. So after the renaming, that's what you're gonna get. Then let's see how we can utilize the SSA after we were able to build it. So we're gonna use key SSA properties, only one assignment per variable, and the fact that the definitions dominate uses. The first optimizations we're gonna look at is the constant propagation. In the constant propagation, we're going to replace all the uses of the form v assigned the constant c with that constant. And similarly, if we have v assigned a phi node where all the parameters across all edges for phi node are all the same constant, just replace with the constants. So this is the standard constant propagation. It's relatively straightforward. We have the working set site assigned as the list of all defs. Then until it's not empty, just take a statement removing if a check has one of the form, then just delete it and replace it with a constant. Other similar optimizations with SSA that can be very powerful is copy propagation. Again, we can just replace the variables if we know that the only parameter for phi is like y, so we can replace all the uses of x with y. We can also use constant folding. In practice, though, things might be not that simple. First of all, let's look how a standard constant propagation would work in this case. What we're going to see is that's the finals that originally generated, as I showed you them before, right? So we need to convert this graph into the SSA form. As you look here, we have several of these variables initially assigned to a constant. So we can start to propagate these constants across the edges. For example, variable j1 has a value 1 here, so that value 1 can be propagated here. And k1 is assigned to 0, so across this edge it can be propagated to this 0. Similarly, the value j3 was equal to I1. I1 is 1 here, so j3 is now assigned to 1. Then if we keep looking, the j3 is assigned 1 here, so that allow me to copy propagate 1 here. It seems like we are moving, but we're not moving well enough. So essentially, after we copy propagate it, nothing is really resolved. None of the 5 functions are removed, none of the copy instructions are removed, not a lot of benefit. So it seems like the straightforward copy propagation won't work that great in this situation. What we need to do is we need to use a special form of constant propagation called conditional constant propagation. So the question I want to ask, does block 6 ever executes? It looks when you look at the graph, it seems like it's totally possible that you can execute it. Depends on the value of j2, more specifically. But is it really the case or not? That's an interesting question. So simple constant propagation cannot answer such questions, but conditional constant propagation can tell. The conditional constant propagation assumes that blocks don't execute until proven otherwise. And it also assumes that values are constants until they're proven otherwise. So how are we going to define the conditional constant propagation? So that algorithm keeps tracks of block, and it assumes that block is unexecuted until proven otherwise. So essentially we had our traditional lattice in data flow analysis that represent non-executed as a top element. So if I've never seen this block being executed, I assume it's not executed. Then if I had an evidence that this block was executed and I had a constant assigned to it, then this constant is the value that I believe it is the only possible value for now. So it's a constant value and it can be any constant. If I have an evidence that the value can have two different meanings in different contexts, that can hold, this variable can hold two different values at different times, then it means it is not a constant and we define it as a bottom element. How the conditional constant propagation will help in this case? Let's try to do it together. So let's look first at this block. We see that in the block J2, we execute this block. Then K2 has the value 0. This is one possible value that we get through this edge, right? So when we're gonna look at this branch, and that's the first branch we faced, 0 less than 100, gonna take this direction. Then we're gonna look at J2. J2 would bring us the value 1 again, going through this path. So this branch again is taken this way. Then we come here. In this case, there is no branch, so we just go through this edge and we go through this here. But there is one thing that's important here. Remember, K2 was 0 here. And we never seen K2 being anything other than 0 because that's the only value we see. So we go from the top to 0 and we assume until proven otherwise that that's a constant 0 here. Then K3 becomes 0 plus 1, it becomes 1. So what happens is 1 is then propagated all the way here. So we get K4 that equals 1 and K5. How about J5 and K5? I've never seen them have any values yet. So I will assume that they can be, top elements, so never executed. Would it help us? Let's have a look. Let's look at value K first. So if that's never executed, and this is 1, so I had to assume that's 1, right? And then K4 is 1, and then I write here with K4 to be 1. So what does happen now? Well, what happened now, I get K4 1, and before I've seen K2 here replaced with 0. So it means that K2 can be either 1 or 0. I had the evidence of it have two different variables. It means that K2 is now a bottom element. It's definitely not a constant. So we can't really do anything with K2. So no luck with K, but how about J? In J, similarly here, we'll get that J is equals to 1, and we get J4 and go with this H. And luckily, we see that J4 is also 1 here and 1 here. So it means that so far our evidence doesn't contradict. J is always 1, which makes J2 1. That means J2 is 1 here. So surprise, surprise, because of all that information, we're able to prove that this branch is never taken. And we can also prove that this return here is 1. And we can also prove that all this code is really not needed. So really, all the values of j and I can be fully removed. And the only thing is needed is this iteration over k. So as you can see, conditional constant propagation together with SA was able to impressively simplify this already relatively simple piece of code, make it more efficient and remove a lot of dead code from it that otherwise was not obvious. Thank you.